So like here, for example, right, for the duration of this interval, right, the cosine function was on top, and then this parabola was on the bottom, correct? Now, what if the boundary of a region is defined by more than one function, right? So in that case, what you have to do is partition the region into subregions that could correspond to the function changes. Okay, so take a look at this one. It says find the area of the region R, and I don't think we've encountered the region R before. Most of the time in calculus, like 99% of the time, the region which you want to find the area of, it's always given the symbol R, right? So here, the shaded region, right? Instead of saying shaded region, it's R, okay? So find the area of region R in the first quadrant, and we all know what first quadrant is, right? That is bounded above, right, by y equals root x. So that's this one here, y equals root x. Okay, so it's bounded above by y equals root x. And below, right, so those prepositions are not there for no reason, for nothing. So above y equals root x, and then below the region, you have the x-axis and the line y equals x minus 2. So if this is the region R, above it you've got this one function, but below it you've got two functions. One is this y equals 0, and then y equals x minus 2. Okay, so if you follow my pointer here, right, if we read that again, the region R in the first quadrant, that is bounded above by y equals root x and below by the x-axis and the line x minus 2. So R is this region inside. Okay. This whole thing, right, it starts at x equals 0, and it goes up to x equals 4. Okay. Throughout this interval, the upper function is always y equals root x. But what's the lower function? Remember how we were doing upper minus lower? And I said to remember that terminology, upper minus lower. So here, upper is y equals root x, but lower, it's y equals 0, and then it switches to that one. So you need to create two regions, two integrals, all right? Right around here, the regions are separated. So what I need to do to find area is, first I need to find the area from 0 to 2, right? And here the top function is root x, upper function is root x, minus 0 dx. And then I'm going to add that area to the area of the second part from 2 to 4, root x minus x minus 2 dx. Okay? So on the left part, I have root x on top, 0 on the bottom. Here I have root x on top, x minus 2 on the bottom. These two are independent of one another. So always, right, just do your due diligence and, just block it off and look, upper, lower, upper, lower. It doesn't hurt to be overly cautious here. Okay? Now, this thing, you don't have to write it as, root x minus 0. You could just write it as root x. So you could just as well write this as 0 to 2, root x dx, plus 2 to 4, root x minus x minus 2 dx. And what we're going to do actually is put these in the calculator today, right? Go ahead and put this in the calculator. So here's what I'm going to do. this side of the room that's closer to me, I want you to put in the first integral, 0 to 2 root x. You guys, I need to put in the second integral, 2 to 4, the other one. So, wait, okay, so for this integral, I get 1.886.
But that's rounded. Right, but that's rounded.
It's okay. It's good enough because the third digit, we're good. Anybody over there? 1.448. Awesome. 3.334. Fantastic.
Good job. Wait, I didn't get 334. I got 334.
Well, if you add the 8 and the 6, that should give you a 4. Here?
Oh, like we're adding the rounds in.
It's okay. This is good enough. This is good enough. Oh, hang on to that. I'll take a look in a minute.
You won't take off points either way.
No. Okay. Now, we're going to change things up a bit. Well, not a bit, a lot. Okay? Not everything is going to be oriented this way, where it's upper minus lower. No, no. Sometimes we can integrate with respect to y. So let's think about this for a minute. What is our variable of integration here? X, x, x. And with the older versions of the calculator, right? This is it. Like when you put in that x, you're telling it that's the area of integration. That's the variable of integration. What does that mean? What does that mean? Remember, I always say this. Remember the people who got you where you are, right? How did we get where we are? We got here by first doing those Riemann sums, right? By first finding the area using the what? The rectangles. So let's just pretend that, we had a rectangle here, right? Right here. How do you find the area of a rectangle? What times what? Base times height, right? And what is the height of this rectangle? Well, or it's y, right? The height is the y. And what about the width? How much is the y? It's a unit in x, right? The width is dx, right? That's the width, okay? So our width was little increments of dx, which we were adding up, okay, over the interval on the x-axis, okay? So the little increments that we're adding up, those were in the x-axis. That's called integrating with respect to x. Now, what if you wanted to integrate with respect to y, right? So sometimes the boundaries of a region are such that they are described by functions of y rather than functions of x. So instead of having y equals 3x squared plus 7, let's say, you will have x equals 3y squared plus 7. Okay? This is a function of y. Okay? Now that, everything is switched. Okay, so in that case, right, to integrate, so take a look at this one. Here I have g of y. This is g of y. And here I have f of y. If before our larger function was the upper curve, why was it the upper curve? Because if I'm looking this way, these are the bigger numbers and the smaller numbers are down here, correct? Well, now here, if I'm looking along the x-axis, where are the bigger numbers? To the right or to the left? To the right. So now when I integrate, I'm going to integrate the function to the right minus the function to the left. Furthermore, okay, I'm going to go from C to D, And now what's the big deal here is that my rectangle now is drawn sideways. Okay? So this is x of y. That's the function. And then this is the dy. And what I do is I incrementally add the little dy's. So you see how when you take this, it was the dx's that we were adding from 0 to 4. Now everything is turned, and it's the dy's that we are adding from C to D. So here, because I'm adding in rectangles along the y-axis, it's no longer dx, it's now dy. This is the biggest change here. Okay? So when it's right to left, you're adding integrals this way. You're adding rectangles this way. So it goes with dy. Okay? All right. And these are y coordinates. So everything is consistent. Okay? Y coordinates. In here you have y variables, and then you have dy. Okay? Y. All right. You think I'm a crazy person yelling all this stuff at you, but like things do get a little bit confusing in the beginning. So let's take a look at this. Find the area of the region that's repeated R in the first quadrant that is bounded above by y equals root x and below by the x-axis and the line y equals x minus 2. Oh my God, where have we seen that before? The last page. But this time we're going to do it by integrating with respect to y. Okay? So now, here's why it's a beautiful thing. So this is, if it's with respect to y, okay, all your functions must look like x equals blah, blah, y, blah, blah. So if this is y equals root x, how can I solve that for x? X equals y squared. And if this is y equals x minus 2, then what's x equal to? 2 plus y or y plus 2. Now, this is the region R.
Yeah, how about the bottom?
Okay, so take a look. If I'm integrating with respect to y, then I'm going left minus right. I'm sorry, right minus left, correct? So look, what's on the right? The red one. Left, the blue one. The red one, the blue one. The red one, the blue one. The red one, the blue one. For the duration, like for the entirety of that region, I have the same function to the right and the same function to the left. So when I integrate with respect to y, I can get away with one integral, whereas here I had to do two separate ones. You see the benefit? You almost see it. You guys don't see it just yet. So what I'm going to do is this. I'm going to go right minus left dy. And here it's y1 and y2. Okay? Right, it is. I haven't put them in yet. So now, what's the function to the right? X equals y plus 2 minus the function to the left, y squared. And now my bounds of integration, it goes from the smallest, from the first y value to the highest y value. So from 0 to 2. From 0 to 2. And then what's the variable of integration? dy. Okay? When you put it in the calculator, you could still put it in as x's. All right, just go from 0 to 2 and see what you get.
Is it possible to have a y?
You switched your letters, your functions. It's y plus 2 minus y squared from 0 to 2.
Oh yeah. Okay.
Yeah.
Yeah, you said I could still use x though.
Yes, you still use x. It's the same answer. It's the same area. It's the same area that you're painting. Whether you paint this way or you paint this way, you're going to use the same amount of paint. So whether you're integrating this way or you're integrating this way, it's the same answer. But do you see what happened? Huh? It's more exact, but do you see what happened that we got away with one integral because the boundary didn't change? Okay? So sometimes you are told integrate with respect to x, integrate with respect to y. Sometimes you take a look at a problem and you go, okay, if I look at it this way, the boundaries are changing halfway, but if I look at it this way, it's not changing, and you choose the one that's easier to do. Okay, so area is 3.334. It's not 4? Is it? Oh, okay. Huh? Yeah. Okay. Let's do this last one. The area enclosed by the graphs of y equals x cubed and this. Okay, so let's take a look at this one. You have y equals x cubed and x equals that one. Right, so you have, okay, so look at this. This is the region R. So now look, if I'm integrating with respect to x, all right? If I'm integrating with respect to x, then it goes this way. And now look, over here, red is on top, red is on the bottom. But if I go here, red is on top, blue is on the bottom. This means two integrals. Not cool. What if I go horizontally? Then if I go horizontally, blue and red, blue and red, blue and red the whole time. So I could get away with one integral. That's the better one to choose. Okay? Yeah. Yeah. Okay? So this means we're going to integrate with respect to y. Okay? Now, if you're going to do it with respect to y, everything needs to be solved for x. So here, x is going to be what? If cube root of y. Which one of those is that? Is that the blue or the red? Blue. And then here, that one's already solved for x, right? So which one's the one to the right? The blue. Okay? And this is the one on the left. Okay, so now, where do these things intersect? Okay, it looks like, right, so it looks like, you know, this might be at -1, but this one, right, I don't know where that one intersects. So we're gonna do it in the calculator. So before that though, let's do this. Let's just set up our integral.
How do we put the y's in here?
I'll tell you just a second. We're going to do it the other way. So here it's going to be y, cube root of y. Can I just say y to the 1/3? That's easier to integrate. Minus y squared minus 2 dy. And it's going to go from -1 to some other number. So now, yes, now you're going to do the storing thing. Maya loves the storing thing. Okay, so, okay, here's what we're going to do. Ladies and gentlemen, in y equals, in y equals, we're still going to put in the functions as y of x. We're still going to put it in as x to the power of 3. No, x cubed. You're still going to put in y equals, right? Because these are all y equals. You're welcome. It doesn't matter how you're writing them. It's still the same function. And then here, right? I need to put this in as y equals. So take a look here for a minute. Take a look here for a minute. If x is equal to y squared minus 2, then what's y equal to? X, ooh, look at you guys. X plus 2 is equal to y squared. Take a square root, plus or minus x plus 2 is equal to y. What's up with that plus or minus? Right? Because look, what does root x plus 2 look like? That. So this is root x plus 2, and that's root x minus 2. They're two separate functions, okay? All right, so let's just put it in with all its glory. I'll tell you. You put them in as separate ones. So you're going to do root x plus 2, and then negative root x plus 2. And then you're going to graph. So here is x cubed. Here is root x plus 2. Here is negative root x plus 2. And I just want the point here. So what we're going to do is this. Second calc. Find the point of intersection. Now look, there are three functions here. So it says, which two do you want to find the intersection of? Is x cubed the first curve? Yes, it is. Enter. Is this the second curve? Yes, it is. If it wasn't, if you wanted the bottom one, you just press up or down and it toggles between the functions for you.
What do you choose now?
Intersect. So you're going to do menu, analyze graph, intersection, and then you don't have to choose anything. You just make the boundaries. So it's 1 point. Oh, we need the y. Now we need the y, right? Y here. Y is 1.793. So this is going to go up to 1.793. You have to write that number in there in order to get credit for that part. Now, second mode or quit. Now, you're going to store the y. Alpha, where's y? Thank you. Store as a. Yeah, you can store it as whatever you want. There it is. Okay, you can store it as whatever you want. You can store it as your favorite letter. So you can store it as your initial. I just did A. You could do B. I know the top one is always B. It's okay. We're spicing things up here. So now we're gonna do math 9. I love calculus, by the way. We're gonna do math 9. Math. You want to do the integral? There is another way to do it on here. You should cry. I'm gonna cry. So we're gonna go from 1 to alpha A, or whatever variable you stored as.
Isn't it negative?
Plus 1.
Negative 1. It's negative 1.
Oh, sorry. I thought you said how do you do 1? Minus 1 to A. And so it's x to the power of 1/3 minus x squared. Now, do you mind if I distribute that negative and do plus 2? It's a free country. You get the same answer. It's thinking. It's thinking. It's still thinking. Why is it thinking that hard?
Hard one.
It's a hard one. 4.215. Here we go. So that's the area. These are amazing. So always put in A equals because I want to know that you know that we're finding area.
Mine didn't work. Wait, mine did.
Okay. So